Hello, my dear students, and welcome back. I know. Exams are just around the corner, and the pressure is on. But don't you worry. Today we're going to tackle this chapter on solar radiation and heat, and I promise we'll break it down into super simple points. Let's make geography fun.
Okay, so let's start with a funny question. The sun is like this massive ball of fire, right? It's constantly sending a huge amount of heat our way. So have you ever just stopped and wondered, why doesn't our planet keep getting hotter and hotter? Why doesn't Earth just cook like a giant tandoori chicken in space? That's a silly thought, but trust me, it's a very important scientific question.
To solve this big mystery, first we need to understand the energy that's actually coming from the sun to the Earth. You know, it's a really long journey for that sunshine, and it has a special scientific name.
And that special name is insolation. Now, I know it sounds like a big, complicated word, but it's so simple. Just break it up. In for incoming, sol for solar from the sun, and ation for radiation. So, incoming solar radiation. That's it. It's just the energy Earth gets from the sun. And a tiny detail to remember for your exam, it arrives in short waves. Easy peasy.
Now, you know from your own holidays that Uti is way cooler than Chennai, right? And Delhi gets those extreme hot and cold seasons, but Mumbai is kind of the same all year. This just means not all places get the same amount of this insolation. So, what's the deal? Why does that happen?
Well, the biggest reason is the angle of the sun's rays. See, near the equator, the sun is almost directly overhead. So the heat is concentrated in a small area, like a spotlight. But as you go towards the north or south poles, the rays become slanted. They spread the same energy over a much larger area, which makes it less intense. Of course, other things matter too, like how long the day is, or if it's a cloudy day.
And now, finally, the answer to our tandoori chicken question. The reason our Earth maintains a nice, stable temperature is because of something called the heat budget. Just think of it like a perfectly managed bank account, but for heat. Whatever comes in must go out. The balance is always perfect.
To make this super easy to understand, let's just imagine that the total energy arriving at the top of our atmosphere is 100 units, okay? A nice round number. So the sun has sent us 100 rupees worth of heat energy. Now what happens to it? You'd think Earth just soaks it all up, wouldn't you? But no! Out of those 100 units, a whopping 35 units get reflected straight back into space. Clouds, dust, even the ground itself just bounces it back. So only the remaining 65 units are actually absorbed.
And this reflected energy has a cool name, albedo. The easiest way to remember this is to think about a hot, sunny day. If you wear a black shirt, you feel so hot, right? But a white shirt reflects the sunlight and keeps you cooler. While snow and thick clouds, they have a very high albedo. They're like a giant white shirt for the Earth, reflecting all that heat away.
Okay, so Earth absorbed 65 units of energy, and this makes the surface nice and warm. But the story's not over. The Earth then starts releasing this heat back out into space. This is called terrestrial radiation. And here's the rule. The sun's energy came in as short waves, but the Earth sends it back out as long waves. Short waves in, long waves out. Remember that.
So here is the most important part. The Earth absorbed 65 units, and guess what? It radiates all 65 units back into space. The amount in is exactly equal to the amount out. The budget is perfectly balanced. And that, my dear students, is why the Earth's temperature stays stable over time. No tandoori chicken for us.
Okay, here's another very, very important idea for your exams. If I asked you how the air gets warm, you'd probably say, the sun's rays heat it directly, right? Well, you're in for a little surprise. The atmosphere is actually heated from below.
The air around us gets heated in three main ways. First is conduction. This is direct contact. You know when you accidentally touch a hot tawa on the stove? Ouch! The air touching the warm ground gets heated just like that. Second is convection. This hot air near the ground becomes light and rises up, carrying heat with it, just like the steam that rises from a hot cup of chai. And the third one is advection. This is just the sideways movement of warm air, like those hot loo winds that blow across North India in the summer.
We all love going to hill stations like Uti or Shimla for the summer holidays, don't we? But have you ever wondered why they are so much cooler than the cities down in the plains? Well, this brings us to our next topic, the different things that control the temperature of a place.
So the temperature of any place is decided by a few key factors. Its latitude, which is how far it is from the equator. Its altitude, which is how high it is above sea level. how far it is from the sea, and the kinds of ocean currents and winds that are nearby. For our UDI example, the most important factor is its altitude.
Now this brings us to a golden rule in geography called the normal lapse rate. Please, please, please remember this for your exams. As you go higher up into the atmosphere, the temperature decreases at a rate of about 6.5 degrees Celsius for every 1,000 meters you climb. And that is exactly why Uti, which is high up in the hills, is so much cooler than Chennai, which is right at sea level.
So how did geographers show all of these different temperatures across the entire world on just one map? Well, they use a very clever tool, and it's really important to understand it.
They use these imaginary lines called isotherms. Again, don't be scared by the name. Iso means same, and therm means temperature. So an isotherm is just a line drawn on a map that connects all the places that have the same temperature. Simple as that. Now have a close look at these two maps, showing the isotherms for January and July. You'll see something interesting. The lines are kind of straight over the oceans, but they bend like crazy when they cross over land. Why? Because land heats up and cools down very, very fast, while water takes a long, long time. You can really see this in the northern hemisphere because there's so much more land there.
All right, my champions, you have learned so much. I think you're ready for a little challenge. Let's see if you can answer a typical exam question on this topic. Don't worry, you know this stuff. You're going to ace it.
Okay, here's the question straight from your textbook. The atmosphere is mainly heated by is it A, B, C, or D? Take a second. Think about what we just discussed, about the sun heating the ground, and then the ground heating the air.
And the correct answer is C, long-wave terrestrial radiation. Yes, I bet you all got that right. This is that super important point again. The atmosphere is heated indirectly from the bottom up by the long-wave energy that the Earth itself gives off.
Okay, before we go, let's do a super fast lightning round recap of the most important points. Ready? Insolation is the sun's energy coming in. The heat budget keeps Earth's temperature balanced. Albedo is the energy reflected away. The atmosphere is heated from below by the Earth. And temperature depends on things like latitude and altitude. Got it? Perfect.
You all did such a fantastic job today. This is a really important chapter, and now you'll understand it perfectly. You've totally got this. All the very, very best for your exams. I know you're going to be brilliant. And hey, don't forget to share this with your friends who might need it. Bye for now, and happy studying.